While some people think having your head in the clouds is a bad thing, others know that vision beyond our extraordinary sphere of activities can yield extraordinary results. We've been involved in human space exploration since the 1960s, when our crafts first penetrated the veil of our atmosphere to explore the cold darkness of outer space. We've achieved many tremendous accomplishments. We've walked in space, docked in orbit, and even put men on the moon. But one field, Bioastronautics, is pushing the limits of humans in space exploration. Their focus is designing better spacesuits. A spacesuit provides the vital barrier between the human body and the harsh environment of space. Spacesuits have come a long way since they were first introduced in the 60s. They now boast a complicated array of physical, chemical, and biological sensors and support systems. Realistic training for the use of spacesuits outside the Earth's environment is also a complicated pursuit, with many considerations such as reduced gravity and the simulation of intense environmental difficulties of being in space. Outside of suits, the crafts that enable space travel and the habitats in which the astronauts must exist have to be carefully engineered to support life. Every normal life function, from exercise to sleep, from eating to waste, from health to sickness, has to be considered carefully in this unusual environment. These associated studies are called bioastronautics.
Hi, I'm Katie Rowan, and we are pleased to have with us today Dr. David Klaus, Assistant Professor of the University of Colorado's Aerospace Department and Associate Director of BioServe. His experience includes research involving space shuttle life support systems, advanced spacesuit testing, and thermal modeling. Thanks for coming, Dr. Klaus.
Thanks for having me here.
So tell me a little bit about spacesuits.
Spacesuits. Well, when I was working on the spacesuits, that was close to 20 years ago, and that was a job I had down at NASA in Houston. And what we were doing at the time was there were two competing new spacesuit designs that were being compared against the existing shuttle suit. So my job was to come up with ways to test maneuverability and range of motion and how much force it took to work in these new suit concepts to compare them against the existing suit and look for improvements.
You've been involved with technology that's actually gone into space. What kind of stuff did you do with that?
So fast forward about 5 years from my initial background working at NASA, and I came to the University of Colorado here in the early days of what we've developed now as the BioServe Space Technology Center. And that is a little bit different. That's developing payloads, that's developing experiments that fly on the shuttle that are taken up to the International Space Station mainly at this point. And those are commercial biotechnology research that are aimed at making use of the space environment for terrestrial advantages in things like developing new drugs, preventing bone loss, looking at muscle atrophy prevention, and studies that are associated with spaceflight but have commercial terrestrial relevance, and they're funded by industries on the ground.
Can you give me a little bit more details about the spacesuits?
So the spacesuits, as well as spacecraft, as well as our little payloads, all have something in common, and that is they're all designed to support life in a rather harsh environment. And interestingly, whether that life is a single bacterial cell or an astronaut in a spacesuit or 6 astronauts in a spaceship, it's almost the same at a functional level. You have to condition the thermal environment so the temperature is appropriate. You have to make sure the pressure is appropriate. You have to provide some sort of nutrient sources and water to the bacteria as well as the astronauts, and you have to remove the waste. So how you do that, of course, is very different depending on whether you're working with single cells or whole individuals. But functionally speaking, it's very similar from an engineering design standpoint at a high level.
You talked a little bit about BioServe. Do you want to go into a bit more detail?
Well, BioServe is a NASA-funded center, and our charge is to help industries on the ground make use of the space environment. We've flown experiments now to date since 1991 on 30 missions, and that's including mainly the space shuttle. We've also launched payloads aboard the Russian Progress and Soyuz vehicles, and we've sent payloads up to, early on in the program, to the Russian Mir space station, and now more recently almost exclusively to the International Space Station on these flights.
What exactly are payloads?
A payload is an old nautical term that is, you're going to take something on your ship that pays the cost of the journey, right? So that's the origin of that term, but really it's just experimental devices that fly on the shuttle that are delivered up into space and they're operated by the astronauts in our case.
You were actually a NASA astronaut candidate finalist. Tell me about that experience.
Well, that was a lifelong goal I had throughout my career. I started out as a launch controller. I was a shuttle launch control and engineer at the Kennedy Space Center, and then worked in Houston for a few years in mission operations, and that's when I did the spacesuit testing. And then coming back to get a doctorate was a step toward becoming qualified to compete in the astronaut selection process. I made it down to the final, next to final cut, so the penultimate cut twice in '98 and in 2000. That's going from something like roughly 3,000 applicants that are screened down to 120. The 120 are then interviewed, and of the interviewed, about 40 are kept as semifinalists at that point, and that was, I think that was over the two times a total of 17 months of waiting to hear the outcome. It's a long process. It's about a year end to end. And of the 40 that I was made into the two cuts there, about 20 or 25 got selected. So I got down close twice. And then the program changed. The utilization of space station plans changed. That was the Columbia accident occurred in that window of time. And so they started skipping a few cycles. They're only just now starting the next interview group again. They picked a class of '04, but that was a little different selection. It had a lot of teacher astronauts in it. The most recent application pool is the first time since 1992 that I haven't applied, because some 10 years went by and I got about 20 years older in the meantime. So.
What kind of qualifications did you need for that?
Most of the astronaut corps still comes from the military, so being a civilian PhD candidate is actually a pretty small number to start with. The qualifications really aren't stated so much as a certain skill set. It's more general. It's being in reasonable health. In fact, the interview lasts a week, and it's almost exclusively a series of mental or psychological and physical exams and evaluations. So pretty much they probe you inside out and backwards mentally and physically for a week. At least you know you're in good shape. The interview itself is only 1 hour. There's about 16 current and astronauts and other administrators in the interview board, and they sit you in a room, they introduce you to everybody, and they say, tell us about yourself, you've got 1 hour. Start with high school. And that's the interview question. Then it's just more informal discussion. So there's not really a magic bullet to get in. You know, they're looking for a well-rounded person with a lot of experience in space flight. So, you know, at that point, I don't know what it comes down to beyond that last cut there.
Mm-hmm. So when did you develop this love for space and space exploration and technology?
You know, growing up, I was always fascinated and seemed to alternate between wanting to be a mechanical engineer and a forest ranger. So depending on what year it was, one or the other was up front. And then as I got into engineering as an undergrad and I watched the STS-1, the first shuttle mission, and I think that's where the intrigue started growing. I used to write to NASA as a kid, well before internet and email made that really easy. And I've got all kinds of literature from the early Mercury, Gemini, and Apollo days, including signed photos of Neil Armstrong, who doesn't do signed photos anymore, I'm told. And so I think it started growing slowly, but it was something that, until I started working in the program, I didn't really see as a real possibility. And then looking back on it, I think that the combination of, you know, forestry and engineering is almost brought together, because it's kind of an exploration plus technology you know, underlying traits there between the two of them. So I'm just as happy to go climb a mountain as I am to build a space payload. And I think somehow those two things sort of converged on this. Maybe an astronaut would be kind of a cool thing to be.
That's cool. You were the recipient of the American Society for Gravitational and Space Biology's Young Investigator Award in 2003. Why did you receive that?
That's a very prestigious award in my opinion, because it comes from peer researchers in that group. The American Society for Gravitational and Space Biology, pretty much as it sounds, that's the research community that does space biology research. And in fact, I was the first engineer to receive that. So it's predominantly a biological sciences community, and there's a lot of overlap with engineering analysis of the gravity-dependent forces that are acting on the cell that I've been trying to develop a model for not measuring what happens, but explaining the underlying causes. So I think it was to do, the award was along that spirit.
How does this all relate back to the curriculum here at CU?
So the curriculum we've been developing, I've been spearheading for a number of years now, is called Bioastronautics. And my short and sweet definition of that is the study and support of life in space. So the study of involves how life responds to the space environment, and the support of runs everything from the small test tubes up to spacesuits and spacecraft. So it's a combined, you can't study the life if you don't support it, but you can support it without studying it. And so from that, I teach classes in space physiology that pretty much cover everything from the person to the inside, how the person adapts to the space environment. And then spacecraft design covers everything from the person to the outside of the spacecraft. So what does it take on the outside to keep the person alive and healthy? And so we're now developing a curriculum that teaches those two components.